this is going to work with some amazing people, right? This is going to work with some amazing people. If I say something that you like, it's because of them. If I say something stupid, it's because of me, and I apologize. And this is mostly work done with Nayung, which sits here. Wave to the crowd. So she's there. So if you ask me about stuff and I don't have a good answer, she will probably give you a much better answer. And Jack, I don't know if Jack is here. Jack here. Anyway, so this is jointly between the two of them. And there's a lot of other thoughts in this talk that come out of discussions with a lot of people. And I also want to say I learned a lot from my friend and colleague, Kang Lee, who taught me everything I know about transformers. And so current language models can do amazing things. So here's a problem from a bunch of mathematicians here. See who can solve this. I can't, by the way. So this is from the AIME dataset, which is like, Jordan, correct me if I'm wrong. It's kind of like a, sorry, I'm interrupting your pizza eating, but it's a pre-math Olympiads type of a thing.
Which dataset did you say?
AIME, the American National. Yeah. So would you say it's pretty hard?
I mean, when I was 16, I was really good at these. I'm probably not now.
Yeah. So they tend to be a little bit harder. And I think they play some role into like entering the math Olympiad. So for sure, GPT-4 level models could not solve it. Okay. So with O1 now, I took a picture of this thing. So this is the O1 Pro. As you have spent $100 to do this. Thank you, NSF. So you take a picture of the problem and you say, okay, solve this problem. And then the model thinks now. So these are the thinking or reasoning models. And after 11.5 minutes, there comes an answer. I'm so bad at math that I wouldn't even be able to verify whether it's correct, but I checked the actual numerical thing and it is actually correct, right? So what goes into solving these problems? So what do you think goes into solving these problems? There's a lot of like step-by-step, right? And a lot of perhaps exploration and self-evaluation and whatnot, which models were not good, but O1 type of models are really good at right now. But these models still struggle with arithmetic. By arithmetic, I mean multiplication and addition and whatnot. So this is Claude Sonnet. The O1 Pro model could solve this. That's why I'm showing you another model. But this is also a frontier model, and I'm asking it, I don't know, like a 6-digit multiplication. And it says something, and it's not equal to the correct result. So these models can't do arithmetic. And I think they can't do arithmetic because they can't extrapolate beyond the training data that they have seen. They can't do harder stuff than what they've seen. And I would argue that this is relevant for math as well, because if you can only solve the stuff that you've seen during training in terms of hardness, you will never be able to, let's say, I don't know, prove the Riemann hypothesis or whatever, which a lot of, OpenAI people think is going to happen eventually. We're not sure. So that's why I'm kind of like curious about arithmetic. So why are LLMs bad at learning simple algorithms, and how can we fix this? And so we started with a paper with Nayung around 2 years ago, trying to understand this, and we're going to a rabbit hole of just like thinking about addition. And so I'm going to start with addition and transformers, the value of textbook data. Why can't we generalize really well beyond the training distribution? So if you train on 5-digit numbers, you'll do really well on 5-digit numbers, but not 10 numbers. We'll try to figure out why this is an issue and why it happens. And then we'll try to figure out how to do logical extrapolation, basically the idea of learning algorithms by self-improvement. Okay. Any questions so far about motivation or anything else? Okay. So we'll focus on a simple setting, NanoGPT, a 10 million parameter decoder on transformer. We're going to use character level tokenizer, which basically means that everything maps to a single token, every number, every special digit, everything that you have in the training data. And the goal is to teach a model how to add. And this is focusing on arithmetic, but I'm going to go to like string operation and maze navigation. I think what I say generalizes. Okay, so that my conjecture is that whatever I'm going to tell you generalizes to like other settings as well. And so I'm going to start with the vanilla training data. So A plus B equals C addition data. And I'm going to train for every prefix of that data set, or every sample, if you will. You see 1 try to predict 0, you see 10 try to predict plus, so like literally for every token. And for most of those predictions, these are not teaching you anything, but at some point it's going to teach you how to perhaps add, right? So for every prefix, I run SGD on the cross entropy of the predicted probability of what the next token is, according to what the model says, given a par. And I'm going to evaluate this against the ground truth. So that's my training set. So that's the traditional next token prediction, cross entropy, blah, blah, blah stuff, okay? Any questions on the data or the algorithm? And the technical details honestly don't really matter, but just at the high level, if the problem setting makes sense. All right. So will the model learn how to add? So this for 3-digit numbers. So the test accuracy is on the y-axis, on the x-axis, the number of training examples. We give it a lot of examples, and even with 10,000 examples, the model kind of struggles, doesn't go to 100% accuracy. So it sort of learns addition on 3 digits up to like 9% accurate, but not really. So that was the first experiment we ran, or I should say Nayunk and Kartik ran 2 years ago. And we're like, yeah, this kind of sucks, right? So this is not good. So the algorithm cannot be taught to the model by these examples. And the first step in our pursuit of understanding this is figuring out why does that happen. So why is there saturation? Why does there too many examples? How can we fix this issue? And so let me ask you a question. Let's say I ask you to add 2 numbers. How would you add them? Well, maybe you'll go, sorry, this it's a little bit too bright. I'm gonna, hopefully you won't fall asleep. Oh, maybe that's okay. Okay. So you would start probably from the least significant bit, right? Why would you do this? I argue it's an easy function to start from the least significant bit, and you would have like carries and intermediate steps and whatnot. And what's the problem with the next token prediction? What does it do? So next token prediction works the opposite way. You're trying to predict the most significant bit first, right? Why is that an issue? Let's see. Why do you think that's an issue? Like, why is this a harder way of solving addition rather than going from the least significant bit? Yeah.
You don't know if there's like a carry digit. Probably.
Yeah, so you have to like internalize the carries, right? So if I didn't give you scratch, but then I give you like a 10-digit number and another 10-digit number, and I told you what's the most significant bit, that would probably be hard, right? So I would argue that the circuit that you need, and maybe Glias can correct, but the circuit that you need to compute the MSB scales as the digits of the algorithm, maybe roughly speaking, or the digits of the input, right? So next token prediction is bad for learning algorithms, at least for arithmetic. And so we're going to play a game now. So I'm going to try to teach transformers how to learn addition with a reverse format. So the most significant bit, first paradigm, you need to know basically everything and internalize the entire algorithm. What if I change the data? So I'll just change the data so that the model tries to predict the least significant bit or digit first. So I changed the format of the data, but I also now say, because of the next token prediction paradigm, I changed the difficulty of the function that the model has to learn, okay? So I changed the problem somehow without changing the loss function or the model by only changing the data. And here's the test accuracy in 3-digit addition. So these are training examples that are not seen during test and test examples not seen during training. And as the number of examples during training increases, the reverse format, which is this curve here, reaches 100% accuracy at still around 5K samples. That's a large sample, but at least it learns how to add 3-digit numbers, okay? So the finding here is that next token prediction is bad for arithmetic. For multiplication, you have the same issues. For other things, you have similar issues. And so the data format can actually simplify the function you're trying to learn. So that's pretty obvious to us at this point. So that was the first finding. When we were like, okay, you can't teach with a normal format, let's reverse it, let's see what happens. It seemed to be working. And you can take it a step further as well and say, okay, what if I trained on like textbook kind of data? So you go in reverse, you take it step by step. So this is kind of like the chain of thought, if you will, type of thing where you produce intermediate steps, right? So now, what the data looks like, and I'm going to compare the different formats. I have like the plain and the reverse, and I have the reverse scratchpad. Like a simplified scratchpad and a reverse detailed scratchpad. And so I record more information here, right? So now what happens? The training happens the same way. So you see input, you see numbers, you see target trying to predict something. You see scratch, you're trying to predict something. But the point is like everything you're trying to predict is a little bit here now. So just giving the model more information, if you will, during the training, but it has to produce many more predictions. So you're trying to learn a higher dimensional function, but the individual components are much simpler, right? So what will happen now? What do we expect to happen for this to, like how will this perform? Again, test accuracy in 3 digits. This is the plane. This is the reverse. This is the limited scratchpad with not too many information. The green curve is scratched with like a lot of stuff going in. And I think at around, 1,000 examples, still a lot, but, at 1,000 examples, the detailed scratchpad transformer learns how to add 3-digit numbers. So that, I think
output looks like that, you're saying?
The output looks like that, yeah. So the model, it's like, you teach the student how to do addition, and then they try to solve it, they will do it the same way that you taught them somehow. So it's going to copy exactly the same style, right?
But is this still next token prediction, but for strings like that?
Yeah. So you predict literally every character here is something. It's like a prediction, right? So like when you see scratch, you have to predict this. When you see this, you have to predict one. This is kind of like a copy operation. So you learn how to copy, memorize, pattern match. Some are in the sort of like process of this. You also do single digit addition. So this is the first digit addition where you add 8 and 7. There is 0 because of the previous carry being 0. And then you produce what the resultant would be, which is 5, and what the carry would be. Just a lot of details about this step. And so the model has to learn all of these things. And then what we judge it for is, well, is the 495, is this number going to match the correct result, right? So we don't really verify if this is correct. It actually tends to be correct, right? We did some experiments on testing the entire correctness of this, and it was close to 100%. But for sure, the correctness of this grows as the example. Okay. So the first finding or the first paper is that data format has a dramatic impact on the underlying function to be learned. I want to talk a little bit more about the COT stuff just for one slide, but then go to talk a little bit about generalization. But let's take maybe a minute break here to see your thoughts on this and if you have questions. When we ran those experiments, I think we were pretty surprised. By now, I think it's sort of obvious that, in hints that this would work. But we were quite surprised by both by the phase transition, which it's interesting, but also that it happens earlier and earlier as you fit more data in the training. As you make your training exams longer, I should say.
So did you try to increase the size of the network?
Yeah, we did some scaling experiments to see how scale plays a role in performance. But what we're trying to figure out first is, with a model that should, it's a model where you could hard code the addition algorithm in the weights. The expressivity is not limiting you from going to 100%. We're trying to figure out what was going on. But part of this experiment was okay, what if you try, increasing the number of parameters, how things change? And I honestly don't remember how that's. What was the conclusion from the scaling experiments?
Our model has better sample efficiency.
Okay. I don't know why this happens, but lots of models were more sample efficient. Yeah.
What's the length of the digits?
So this is just 3 digits. But if you were to train for more, for logic, the same thing roughly would happen. In fact, we saw this 1,000, how does it move with regards to the length? As far as I remember, it doesn't move that much, basically. So it's kind of it learns something local that's generalized beyond 3 digits. When you train on 4 digits and 5 digits, the extra effort you'll spend for the additional bit, for the additional length is not like a multiplicative, it's just like an additive thing, if you will.
But how well does it generalize?
Oh, yeah, great. Okay, so that's what we're going to talk about. This figure basically says that it generalizes in distribution, right? So if your training distribution is the same as the test, with regards to the length, we're good. But we'll see if it's generalized beyond that. Yeah.
So is this a random initialization start?
Yeah, good point. So this is training from scratch, random transformer training from scratch. It doesn't know language, right? So it has not been exposed to anything like this.
Yeah. So that first evaluation point, where it's already at 60%, is that at 0 steps, or is that a little bit more than 0 steps?
Sorry, what do you mean?
At the
here?
Yeah.
Oh yeah, it's it's more. It's not 0 steps. It's whatever this number is here. Yeah. So you start from 0 with. Other question.
Yeah. You tried this, but what if we look at the training?
Oh, okay, yeah.
Shift, right?
So basically, what if you asked what is the training efficiency of the COT, right? So, what is the test accuracy versus number of training tokens? The simplified scratchpad wins, but the detailed scratchpad is a little bit worse. So this is in the paper, and it was part of the slide, but I felt it was maybe second order. So I didn't include it, but that's a good question. What's in terms of training flops, which one is better? That's a very good question. Okay, so why does COT help? Okay, so this is kind of what I mentioned before. The standard format forces you to learn an algorithm without seeing the intermediate, if you will, sort of snapshots of the variables and whatnot, without seeing basically the algorithmic trace. the COT format shows you the algorithmic trace. And what we observed in a paper that was sort of on the boundary of mechanistic interpretability, we saw that the model, when you train on COT, basically learns to focus on small, like it pays attention to a small subset of the input and sort of like filters out everything else, and effectively learns a local rule for this sort of small subsets of the input. So that's from a high level idea why COT helps. There is a ton of work in thinking more about this, and I don't have time to talk more about it, but I want to go back to the question of easy to hard generalization. So like, does NanoGPT know how to add? Does it basically, can it perform the addition algorithm? So you train up to n digits. Let's say that n is 100 or 1,000. Like you train a lot, not just up to 3. Can you do n plus 1? Just like one more, like, n plus 2 digits and whatnot. So this is what people call length generalization, being able to generalize beyond the lengths you're using during training, or easy to hard. So you're like, you train on, I don't know, you're on first grade and you want to see if you can solve second grade problems somehow, right? So that's the idea of easy to hard. Yeah.
So there's a question in the chat that what if your scratch pad has incorrect steps?
As what?
Incorrect steps in it.
Yeah, okay, good question. So if your scratchpad has incorrect steps in it, you still stand to learn because you're given more internal state as you increase the context. But it has, it's going to impact how fast learning will happen. Depending on the amount of incorrectness of the scratchpad, you'll see different curves. But even if it's completely incorrect, your model is still more expressive because it has more space internally to represent stuff. Okay. I hope it addresses the question that's up. Okay, so easy to hard generalization. So length generalization is actually hard. So transformers don't learn algorithms, they learn shortcuts. So here's an example where you basically, we have 2 4-digit numbers, we feed all the correct results up to the end. The transformer doesn't even have to do all this. And we're like, okay, just do the last step, right? So the last step literally amounts basically collecting stuff here and copying it in the output, all right? And doing like one carry computation. And the transformer fails to do it. And this is, you could argue that this happens because we only train on 4 digits. This is actually, this is a universal phenomenon. There's people that have been thinking about this length generalization for 3 years now. And the first question that I would ask myself at this point is why would we not expect this to happen? So the transformer overfits to the patterns of the training data quite a lot. And there is sort of like a good reason why this happens. So the reason why this happens, I would argue, is related to the positional embeddings. Okay, so what are positional embeddings? So when you have 2 numbers to add, so think of this like as solving the token. So every token is assigned to like one position, right? So the first token has a positional embedding that's, encoded as 1 and so on and so forth. So think of this as being like some function that is added to the embedding of the token 1 and the token 5 and so on and so forth. And all of them have different ones, right? So imagine now I didn't give you numbers to teach you how to add, but I gave you a number and some embedding space plus some other weird thing that's not associated with anything else in the positional embedding space. That is a hard function to learn. Okay. So basically, addition for transformers effectively means that you have to teach only, so this is the ith digit, right? So like if I want to compute like the first digit, think of this as computing a function on the embedding of the first digit for the first number A, the first digit for the whatever number B, and attach to it a positional encoding that kind of like is a function of I, and it's a weird function of I for the other. Like there's a relative thing going on that you have to. So if those things here are not tuned for addition, you have to learn to overcome this really weird thing that's going on here to learn addition. And nobody in the right mind would think that SGD would convert to this. Basically, SGD would never learn this, no matter how many examples you see. Okay? And by this, I mean, like, what would, like, imagine learning this for I equals 1. Why would you know what it is for I equals 2, right? It's like a completely different function somehow. So let me pause here just to like see whether this makes sense. So basically, again, addition is easy for us because there's like all the semantics baked in. We know number system. We're like, we don't. It's the same function for us to add the 8 here with the 1 here and the 9 here with the 5 here. Nothing changes, but the transformer is not grounded in nothing. When you change from scratch, this won't work. In fact, this doesn't even work for Claude Sonnet 3.5, which according to Dario Amodei costs tens of millions of dollars, right? So you can't throw more money at this problem. Something has to change.
So I think even for in-context learning, because similar issues, people used to, I mean, at least for this kind of synthetic experiment, we're used to add X and Y in a single token.
Yeah.
And that kind of get rid of this kind of with two different embeddings.
That would probably, so if you were to stack, the ith digit of A and B on the same one, it probably would work. Yeah, I would expect that this to work. Yeah. I guess the thing I want to do here is like stay also as close as possible to what people run in practice. And I want to talk a little bit about how people have tried to mitigate this issue by effectively overhacking the data formats and the positional embeddings. So there's still a way to like overcome this, but it's a way that's not, I would argue, general purpose. Yeah.
Okay, I have a very naive question because I actually don't understand what's on this slide. AI and BI are digits, right? Those aren't the whole.
Yeah. So think of this as, in fact, let's make it harder for the transformer and maybe for us to understand. But this is like the positional embedding associated with token, whatever, BI, positional embedding of token associated with AI. So think of this as like two vectors.
Right.
And so the number 5 is always the same vector, but depending on what position it's going to be a different input somehow.
So why do you say it's a complicated function to just like forget most of the coordinates and pull out just the coordinate that's AI? That doesn't seem that complicated.
Yeah, I agree that there is a way to overcome this. I would argue it's a harder way to overcome this than just overfitting and not have to do it basically. So what you're saying is like, there's this issue, but like, maybe there is certainly a way to overcome. There is a function. There's obviously function. If you take this as an input, can produce a correct result. What I'm arguing is that yes, you're right, but that function doesn't length generalize. So you learn how to do this for like digits 1 and 2, but when you see a digit like whatever here, or I guess here, with a new positional embedding that you've never seen, like why would you ignore this, right? There's like from the perspective of SGD, that there's no good reason to learn something that generalizes the positional embedding that it has never seen in its life, right? So that's maybe the takeaway from this. Okay. Any other question on this slide? So just explaining why it's hard for transformers to learn these things that are easy for us. Why it's hard to do length extrapolation.
One last question. So do you have any actual theoretical research that shows that SGD prefer anything that's generalizing?
No, but we don't have any result like that. But I would be very surprised if it's not true. I guess that's what I'm saying. Yeah. So this is not a theorem, obviously, right? But it's not like a. Yeah. It goes against my world model somehow. If that was that. Yeah. Okay. So basically the full algorithm is more complex than a fixed addition. So basically what this learn is like just the addition map here. And these are very easy functions to learn. They're like, they're rank 2 functions, and they're super easy to learn up to particular digits. And so this is effectively what the transformer learns. And so it implements pseudo algorithms. It implements shortcuts, doesn't implement a real thing. And people have been trying to fix this. There's 2 kinds of approaches. So there's like the custom embedding approach. I'll talk a little bit about this. And my favorite in trying to overcome this with architecture changes is Kank's paper, Loop Transformers for Length Generalization. I think you talked a little bit about it in one of your talks. So I'll just there's one slide about this. But the first idea is, well, okay, let's try to fix the immediate problem. We know it's because of the positional embeddings. Let's try to fix this. So this is a paper by Google DeepMind. Transformers can achieve length generalization, but not robustly. And so what is here is basically the data format, the type of positional embedding, the name of the person that did it, and we'll focus on what the paper did, which was basically give explicit indexing for every one of the digits of your numbers. So the least significant bit will always be C, the second one will always be, and the MSB will always be A, roughly speaking. Okay. So I always attach this letter to both of my integers and the resultant as well. So that's my training data looks like that. I would argue this is trying, it's kind of like overhacking things a little bit, like it's trying to fix the problem, and I would argue the wrong way somehow. And they also use a relative positional encoding, which is basically adding a square matrix that creates effectively these embedding vectors that are relative to each other somehow. And this also has to be kind of like a learned complicated function. I would argue that both of these, so these are fixes. We'll see that they sort of like fix the problem. I'll explain what I mean by not robust. And I would just argue that these are things that you won't do in practice. So like if you want to train like an actual language model, you won't choose these positional embeddings because they're like tied to these types of problems. And you'd certainly not present your examples like that. Okay. I'm not being critical, by the way, of sort of like, what they actually said. I'm just saying, why was this paper not a solution to the problem of length generalization? In terms of numbers, I don't know if I can focus a little bit more here. Yeah, so basically the red line is what they did. They trained up to, yeah, so this is our paper. This is where the worst here. So this is with the COT. So basically, if you do the thing that transformers do in practice, so you train a normal COT data, you don't try to overhack anything, it doesn't length generalize. So they trained up to 40 digits, and they saw length generalization up to 100 digits, but then it started falling. You can see a little bit of the decay. But this was a good approach, right? So this was kind of like saying, okay, forget about generality. Let's just figure out how you can solve the solution to it. There were a couple of more papers in this line of work, which was basically the idea that have not relative positional embeddings, but positional embeddings that somehow couple things. They couple the first digit with the first digit, the second with the second, and you don't have these weird index hints. I would say that this is, with regards to the data format, the right direction. With regards to the positional embeddings, even more deeper in the rabbit hole of overhacking them. Okay. And so I like this paper. I'll tell you why. I like the previous paper. I like all papers. I'll tell you more about this paper. I like this figure a lot. Not because our thing is still the worst. But I looked at it and I'm like, something here. Okay, I'll tell you more about ours in a second. But so they managed to actually length generalize even more. So they trained up to like 30 digits and they went all the way to whatever, 200. You would never add 200 digit numbers, but let's say you were interested in that. So they sort of like, with this addition on the positional embeddings that was coupling things together, it was like locking the positions together. They were able to overcome this. And of all this work, I'm biased because I think Kang is awesome and I learned so much from him, but also it so happens that this is the most generalizable thing that I've seen in length generalization, which is basically, well, don't overhack the data format, don't overhack the positional embeddings. If you're trying to learn an algorithm, what an algorithm does is basically iterate over the same fixed point iteration. Compute the ith digit addition, compute the carry, and just repeat until you're done. Well, what if you were to hard bake this in the architecture? What if you were to basically have a loop transformer that was trained on addition type of problems? So what they found is that actually also length generalizes quite well. Sorry, I'm not doing a good job at explaining all the technical details, but hopefully this is good enough. So I would argue that's a lot of progress that has been made. But I would say that it's still, the length generalization is still open because for me to close, you have to be in the same paradigm. Vanilla transformers, vanilla sort of like, training pipelines, whatever data people would use in practice. And I'll go back to this figure. I'll tell you why I liked it a lot. So I kept staring at this at some point, and I'm like, maybe we shouldn't be too harsh with our original paper because there's a little bit of length generalization. So you train up to like 30 digits, and the model does well on 31 and 32, and then it just completely crumbles. And I start thinking about this. In fact, I wish I could share. We have a signal conversation with Kang about this. I'm like, dude, I think I'm having a brain fart. This is so obvious. Why did nobody try this? So there's this really cool effect. It's called transcendence. So transcendence is this idea that, yeah, you're trained on data of a particular difficulty, and you're really good at that kind of data, so you're good at n-digit addition, but your abilities extend to a sphere of hardness slightly outside of your training distribution. Okay, so people call this transcendence. There's a very cool paper about this. And so the idea here is, well, okay, I will not sample from the correct addition algorithm for more than 10-digit addition, but I could use the model itself to label examples of hardness slightly more than what I've seen in the training data. And then I could train on that data. and get more data for a problem that's like slightly harder. And hopefully what will happen is this transcendence phenomenon is going to keep happening and happening and happening until you basically learn the algorithm, right? So until you basically learn addition up to whatever, 500 digits or whatever people care about, right? So this is the idea of self-improvement that I want to talk to you a little bit about. But before we move on, I know that I kind of like, said too many things in the past few slides, so I'm going to stay here for a few minutes to see if we have any questions. Yeah.
So in practice, besides the fact that it's like not widely used already, are there reasons to not use loop transformers if they are better in these certain scenarios?
If you ask me, I don't think there's any reason to not use loop transformers because I'm emotionally too invested in them. Yeah, I don't have a good answer. Yeah, I think so. I think where maybe it's development, but here's what I think happens. When you use a loop transformer, you still the number of weights that you have are the same as are lower than a equivalent model that has, instead of loops, like actual weights. So you have less weights than a model like that. But the problem is in terms of like the key and values that you produce are basically proportional to the actual layer. So somehow in terms of like compute and memory, it's not cheaper than a normal layer. It's in fact more expensive. And sometimes it seems that like, for other tasks, not necessarily algorithms, not doing weight splitting and like there's a higher exchange rate on press weights for accuracy in some tasks rather than doing loops somehow. But that's my estimate on why people don't really use them. But I feel they could be part of the landscape. I want to think more about it. Let's talk about it. Okay. Any other questions? Yeah.
All right. So the sentence that you mentioned needs firstly that you train in sufficient digits like 30, or
no,
the original paper that
you can go at some. It doesn't happen if you train on 2 digits, but if you do 5 digits, there is a threshold that below that doesn't happen as strongly, and above that, above that threshold, it's much more present. But it's not like 100 digits.
And if you train 100 digits, does this extend to?
Great. Yeah, really good question. Yeah, the short answer is yes. So let's talk about this in a second. Yeah. Yeah.
So I'm curious. I mean, the way you've set it up is about digit sequences.
Yeah.
Have you done it on any items where somehow it's not naturally a sequence? So the sort of n plus first use case is not sort of doesn't have the nth case as a subsequence. I mean, I guess I'm thinking of like I do a lot of problems like n by n matrices. Right?
Yeah.
Then somehow the n plus 1 by n plus 1 matrix, if you sort of list the entries in a row, it doesn't have the
that's a very good
question. Subsequence.
Yes. That's a very important question because if we were only somehow limited in length, I would argue that maybe the results, the world model we're building through these experiments is probably not accurate. But we did try it on mazes. So the way that we did is like you can fix a maze of, let's say, 100 nodes and start increasing the solution of the maze. So it's like one, or like, think of it, not even a maze, like you have a planar graph and you're like, find the shortest path between A and B. And in my training data, I can have solutions that are like 1 hop, 2 hops, 3 hops, 4 hops. And I want to see if I can hard generalize to the one more. So why is this hardness generalization? Because like for every step of the shortest path, you have to internalize the search that you would need to create the next step, right? So I think the answer to your implied question is yes, that this actually does generalize to like easy to hard type of stuff. I partially convinced myself about it, but I want to talk about it more in the. And I actually want to ask you about like how could we set this up in a controlled math setting where you have axioms and you build theorems that are of given length of depth based on those axioms, and how you can train on like a small easy set and sort of like hard generalize, if you will. Okay, let's go back to this in a second. All right, cool. So can we solve things without changing architecture and positional encoding? I guess I gave out the answer that we can use self-improvement. And it's so none of the stuff we do is new. I'm not saying here's a new algorithm. I'm saying this was so like in our eyes that I'm so surprised people haven't tried yet. So the idea of self-improvement is very simple. You use your model, your language model, to generate data for you. You need to have a mechanism to filter that data between positive and negative examples. Ideally, you would like the filtering mechanism to be much, much, much cheaper than generating solutions. And so the idea is that by training on self-improving data, you can actually, on self-generated data, you can actually improve on your own without getting access to ground truth data. And this idea works really well on, again, places or settings where what they call the generator to verification gap is big, right? So what I mean by that is like proving the Riemann hypothesis is really hard, but if it's written in Boolean, you can check if it's correct or not, right? No matter how long the proof is. So I would say that our algorithm is very close to things like the REST algorithm by DeepMind, to star, which is very popular as well. I would argue what sort of is used at DeepSeek, if you will. There were also a lot of cool papers that are very close to this idea of easy-to-hard generalization. This is the paper with Jordan and Francois, where you did it to problems that I don't quite understand. But I think one of the high-level ideas is sort of similar. With self-improvement, you can solve harder and harder stuff.
No, you definitely just described that paper, like your description includes that paper for sure.
So basically, and also DeepSeek R1, so people are going crazy about it, and there's a good reason for it. It's a very simple technique that they use to take a model that already has a rich solution step vocabulary, it already speaks the language of reasoning, but you use self-improvement to sort of sharpen those skills towards solving particular problems where you can have a hard verification signal. So this is the TLDR of what the DeepSeek R1 is doing. I would argue it's like all of these things are in the same family of algorithms and methods. And sort of I'll tell you the specifics of our algorithm. Again, it's not, we haven't even given it a name because like so similar to the other things. I'm not even taking credit for it's just like the simplest thing you could do. So you train your model on a particular set of problems, let's say n-digit addition, or like solving with shortest path mazes of size 100 by 100 where the solution is like 5 steps or whatever. And then you generate problems, and this is the key part, you generate problems on the region of transcendence, all right? I know that my model can't solve a billion digit addition, but I know that it can solve a little bit outside of the training data. So I collect data and predictions on the boundary of its capabilities. And I use the model to label it, but I want to make sure that I don't train on basically data that are incorrect, all right? And I want to do it in a way that doesn't really use, let's say, the algorithm of addition to figure out which data points are correct or not. So we have a very simple filtering method for filtering out sort of the mistakes, if you will, or the data generated by the model that are not correct. And the idea of this filtering method is that it uses something like self-consistency, where we have parallel models that we run for this, and the mistakes are non-overlapping. So it's kind of like easy to figure out through majority votes which are your correct data. And the other sort of very weak verification signal we're using is if your result is shorter than a digit, we throw it away. It's kind of like saying, if you gave me a proof for the Riemann hypothesis and it was 5 lines, it was definitely incorrect. I don't even have to look at it. So that's kind of like the same idea for addition as well. And so we collect the data and we train on it. The size of the data set doesn't change. The composition of the data changes. And we repeat this for our self-improvement rounds. This is kind of like how the composition of the data looks. So it's kind of like 10 digits addition, split it in half at 11 digits addition examples, split that part in half and add 12, 13, and so on and so forth, right? So at every step of the self-improvement round, I generate data from my model on policy, if you will. I filter them with something very cheap, something that's much cheaper than the addition algorithm. And I keep kind of like training. That's what the algorithm is. And there's a lot of tuning that goes into this for things to work out. But the idea is that this works. So we tried this super simple algorithm. Again, there's nothing sophisticated. It's like the simplest thing you could ever try on a bunch of things. So we tried on arithmetic, we tried on string manipulation, we tried on both normal, like forward addition and reverse addition, and one we know it's harder than the other. And also for the maze stuff, where the difficulty is the length of the solution, if you will. And it sort of works. So the first example was like after I had this signal set with Kang, I'm like, yeah, this either works and I don't understand why people haven't tried or it doesn't work. So then Jack and I ran an experiment where we trained up to 10 digits of addition, and then we did like this simple technique of collecting data from the model and kind of like keep training on it. And we saw that it works up to 20 digits. And I'm like, if it works up to 20 digits, it probably works like more than 20 digits. So this is a 100-digit addition. So you can basically start from, I don't know how many digits we changed here, let's say 10, doesn't really matter. And each line here is the accuracy of every self-improved round for the different digit lengths, right? So this is one self-improved round where its accuracy drops for like 63, whatever its lengths. And this is, the next one and the next one and the next one and the next one. So darker color means like more rounds of self-improvement. This is the same model. These curves correspond to the same model, okay? It's the accuracy of the same model, but when it has gone through another round of self-improvement. So it's not like having new models, just like one model in this case. And the main point of this is you view this as a black box. This model has only seen 10-digit addition examples from outside, right? Everything else is self-generated, okay?
I have two questions. One, what is that disconnected component where it goes down and then up? What's happening there? That's a minor question.
Najim will know. I have no idea.
Okay.
Maybe a failed round, but yeah.
Yeah.
Is that what it is? Okay. There.
But my main question is, let me see if I understand. I mean, you say it's the same model.
Yeah.
But I mean, to get 100 addition, you have to do sort of a certain number.
Yeah.
And if you want to get 200, I guess what I'm asking is, I can write an algorithm that will add digits of any length.
Yes, that's right.
Do you think it ever gets there, or do you think there's always each iteration gives you some ability to add up to some finite? I mean, those are different things.
Okay, so if you train a transformer from scratch, I don't think it's going to get there. But I think that the gap will increase. I'll show you a slide on this. So you can have something like exponential self-improvement. I'll talk to you about this in a second.
Sure.
But if the model does not have any grounding on what algorithms are, what numbers are, and what not, it's not going to happen. But I think for a model like O1 and R1 and GPT-4, if you do this, it's going to effectively learn it and be done. We actually have examples on pre-trained models where the improvements you get are significantly better than just training from scratch. So like all the background stuff matter a lot. Like all the other stuff that you can ground your algorithms on matter. Here, this is hanging in space. It doesn't know anything else, right?
I guess let me just add one more. I guess one of the other papers that Dimitri mentioned earlier in terms of the embedding hacking, they actually proved that there doesn't exist transform without hacking embedding that does generalization addition for any number of digits.
There does or does not?
There does not. That's why they found that if you want to have a transformer that does addition for any number of digits, you have to hack it. But with this kind of thing, it probably can converge to something really large number of digits with a few rounds. Yeah. But I don't think that's what they proved.
Once we reach 10 to the 80, we're done anyways. Yeah. So you'd stop at some point like that. But okay, so you can learn reverse, and then we tried on a bunch of other things. You can try. There's like this other operation that people tested for length generalization, which is like the string, copy the string. Here's a string, reverse a string. I'm just showing you similar figures. The interesting thing here is like at some point, it kind of clicks and it sort of does length generalize. Like the slack of transcendence increases with the number of rounds for some problems. And the conjecture again is that this happens when the sort of like the operation you learn is like very local somehow. Like every step is just like a local thing that only has to look at like two other digits. Yeah.
So this means that like if we train up to 60, stop there. Like we run out of GPU credits or whatever, right? We cannot do 100.
Yeah, I thought when you take out your calculator and do addition there. Yeah, basically that's true. I mean, so the point is that
it never learns.
You have to, if you're a pessimist, it never learn. Yes. But I mean, I'm not going to defend it. Yeah, it never learns the way that we do, right? But if I were to conjecture, if I'm allowed for a conjecture, I would say that R1 and O1 and all these models can do addition for arbitrary digits if they're allowed to do like chain of thought and stuff like that. Maybe not forward. I mean, forward for sure not, but the rest of the things they put, right? So I guess the point is like, can the model learn at some point to just repeat the same steps just for lengths that are longer than what it's in during the training data, right? And I think actual language models could. Testing that hypothesis is a little expensive. Yeah. But I honestly, just going back to math, I think the point is like, well, okay, you train on a bunch of things, but maybe the Riemann hypothesis is like 1 terabyte length of a proof. If you've never seen 1 terabyte length of a proof, you'll never be able to do it somehow, right? So the hope is that by slowly doing like this curriculum thing, you'll be able to do more and more complex things. I'm not saying that you could do the very hard proof, but the idea is that you can't expect to zero sort it if you don't do this continual curriculum of self-improvement.
Does the stack keep increasing?
The what?
Like, does the stack keep increasing? It's like, let's say you for this model, I don't know, if for instance, if you had like 98 digit numbers, can I randomly ask you to do 102 over time? Does the stack keep increasing?
Yeah, the slack for some problems it keeps increasing. So I'll come back to this. Yeah. Yeah.
So what if you have some generated pseudo data that might be locally correct enough to pass your filters, but that isn't globally correct in the aggregate? Thinking, for example, about using transformers to solve large homogeneous linear systems with boundary conditions where we want to avoid lapsing all zero solution.
I don't understand the question. Like if the chain of thought has mistakes, basically is what
I think it's like locally correct to pass the tutor, but isn't globally correct.
Oh, that's probably bad. Yeah, that's probably bad. I mean, you still stand to learn something, but yeah, I don't know. I can't give a definitive one. If I had to bet, I would bet, but this is probably not really good. All right.
Like the that you were talking about.
Yeah.
Is like a general way of thinking about that for a class of
the
problems.
So there is the answer is yes. So I'll come to the filter, but the answer is yes, that you can, and that's like sort of like the goal now for all DeepSeek stuff and using RL in post training, figuring out that SIP verifier, a verifier that SIP can always work somehow. So that's actually a very on point question, very good. All right, so we tried. I have 8 more minutes. I don't want to go into the details, but we tried on forward addition and multiplication. These are really hard tasks. And on maze solving again, where the difficulty scales is a number of with a number of sorts. Sorry, the number of steps or hops of the shortest path. And sort of like one point I want to make is that we observed pretty early that if you like this idea of if somehow in your data collection process where the model labels stuff, if a mistake creeps in, that's a really bad mistake. It's not like uniform noise because the mistakes of the model are very low dimensional, very particular. It kind of makes mistakes where it just always drops the same digit. And sort of it overfits really quickly on those mistakes, and it always says the same thing no matter what self-improvement round you do. So if your accuracy of your sampling or the accuracy of the things that you sample or you generate is lower than some threshold for every task, you are going to see an avalanche effect where just this whole thing dies. So this is very critical to be able to sample correct stuff. And so talking about filtering, I'll skip these 2 slides and kind of go here where, again, you have to do it in a way that's cheap. You have to do it in a way that's cheaper than generating data. And so for addition, for example, and for maze and for multiplication, length filters work. So length again means if your solution has an unexpected characteristic that you can use as a certificate of wrongness, all right, then you use it as a filter, right? So that's kind of length plays that role. Again, for other things for the AI media dataset that we saw in the beginning, you can check the numerical answer, right? So if the numerical answer at the end is wrong, then the whole thing is wrong, right? So the idea is that you won't have a weak verifier, right? Ideally, you would want this to be, you would like to do this even without a verifier. I think that's where the next scaling dimension will be, where basically, and we kind of see this for some experiments where there's this weird thing that happens where the model, you run 5 models in parallel, and then what happens is that you look at you generate examples, and the mistakes are non-overlapping somehow, and the correct stuff are overlapping. So you can do things like majority to basically filter out mistakes as well without having a verifier. So this again trying to observe patterns that happen in the model or the data that are signatures of mistakes somehow, and we want to filter them out cheaper than generating data from the source. Okay. I'm going to skip all that. And I want to talk about this idea of accelerating self-improvement, where the slack of transcendence, if you will, increases. And we saw this happening for addition, for sure. It doesn't happen everywhere, but for addition, for sure, if you have an oracle that tells you all the positive examples that you could label for n+2, n+3, n+4, blah, blah, blah examples, lengths, and you put all these in a data set. So you use kind of like a stronger verifier now, right? What will happen is that the model will learn faster and faster and faster. So like you can start from like doing +1 digit and then +5 and +10 and +100. So it's not provable exponential, but this is pretty rapid increase, I would say. So this is kind of like the performance. How many digits can you do as a function of number of self-improvement rounds? I wish I could tell you more about it. There's no time. And the last thing I want to mention is that if you start with pre-trained models that are grounded in stuff, and it's not just trained from scratch, you actually stand to benefit a lot. So this is the number of self-improvement rounds, the length above, or like I should say, the maximum length that you can do addition. And the different curves here are like, training from scratch. This is the purple curve. And this is using models of increasing size. So this is llama. The orange thing is llama 1 billion parameters, and this is llama 3.2, 3 billion parameters. So what's the finding here? From a high-level perspective, starting with a strong model, you're basically getting something that's more amenable to learn faster, okay? With this sort of self-improvement type of method. All right, so I will conclude so we can chat a little bit more. But I kind of feel, okay, so the first thing I want to say is like, I feel good about saying we solved it. I've been working on research for many years. I don't think I've ever said we solved it. I feel like we solved it. Length generalization, for at least as far as I'm concerned, can be solved through self-improvement type of methods. I'm not taking credit of the method, and I'm not taking credit of anything else apart from just noticing that it works. Okay. And so you can ask if these findings matter, because at the end of the day, you can just throw more money and GPU flops at GPT-4, and this will learn actually 200 digit addition at some point. In fact, GPT-4 is good at 200 digit addition. But I think we learned actually quite a lot from these experiments and these sort of 2 years about, or 2 years of thinking about arithmetic. So the first thing is that, the data matter quite a lot, because the next token prediction is just a bad thing to optimize. It's a bad paradigm if you don't think about what the data format should be. And in fact, the data format changes effectively the functions that you have to learn, right? And in spite of the fact that you can make things really sort of like spelled out for the model and you can train on chain of thought type of stuff, current language models learn shortcuts and they don't really extrapolate beyond what they can currently do. But I think that easy to hard generalization can be solved to some degree with self-improvement. And I guess you don't have to believe me. You can also see basically what DeepSeek did, which is basically something very close, right? So doing this gives you a significant edge with regards to accuracy without wasting too much in training flops. So I'll just end with a bunch of questions. So this is work that was done 100% here at UW-Madison, in spite of the fact that the last year I've been at MSR. The stuff I've been thinking about, both with my group and in Madison and MSR, is basically how do you build reasoning models? What does reasoning mean? What's the role of RL and verifiers and all that? It's a super active field, but it's also super exciting because kind of like at the frontier of, it brought us at the frontier of capabilities. So I'll just end with this, and I would love to chat more with you.